Hello everyone. So in the last class we started looking at the linear mass balance equations for different units. We started with mixture, then we looked at splitter, then reactor, and finally towards the end of the class we started looking at the flash unit and we have solved one example. So just to continue from what we have left in the last class, as we said in the last class that the uh, linear mass balance equations for the flash units are extremely important, primarily because these are also used in different operations like distillation and absorption. So in the flash unit what we have seen is uh, so how we can represent the output from the unit in terms of the split fractions that we have seen in the last class. So how the input in the flash unit can be represented in terms of the output using the split fractions that we have seen. And again, what we said is in case of flash unit, the for the linear mass balance there are two degree of freedom. So either we can have uh, either we can have the split fraction epsilon zeta n specified and p or t specified. With this we can completely write down the flash unit equations. So you can see that the procedure which we have discussed in the last class is, if the split fraction zeta n and p or t is known, in that case what we do is we calculate the equilibrium constant for the key component, then we calculate the relative volatility of the component with respect to the key component, uh, and then we calculate the split fractions for the different components. Remember, the split fraction only for the key component is specified, but the split fraction for other components we calculate by using this equation. And once the split fractions are obtained, then we calculate what is the molar flow rate uh, of the components in the vapor phase as well as in the liquid phase, and their mole fractions. And once we know these mole fractions, then we calculate the average value of the relative volatility, and with the average value of the relative volatility then we back calculate the pressure. And if the pressure is fixed, then we back calculate the temperature and we check whether this particular temperature is satisfying or not. If it is not satisfying, we repeat this particular calculation iterative manner, so that both assumed values and the obtained values from the equilibrium relations are matching with each other. In case 2, instead of taking the split fraction fixed, in case 2 we take pressure and temperature specified. Remember, in this case we have uh, 2 degree of freedom. So in this case, once we take p and t fixed, we assume the starting value of the uh, split fraction of the key component, and with that again we repeat these steps 2 3 4, and then finally again we calculate the average value of uh, relative volatility, and based on that we again back calculate pressure, and we check whether this particular pressure and temperature are satisfying or not. If they are not satisfying, again we go back and make another guess for uh, the split fraction for the key component. In the third case, either the factor phi or p or t are specified. So in this case again we back calculate the average value of the uh, relative volatility, and then do the back calculation to find out t and p and see whether these are matching or not. If they are not matching, then we again repeat the calculation. This is what we have seen in the last class. Now we wanted to extend the same analysis for another unit. So in this case we are going to look at the distillation unit. So in distillation unit, we can see that it can be considered as a cascade of equilibrium trays, where each tray can be considered as one flash unit. So all the equations which we have seen for the flash units, uh, we will be using some concept of that for writing the mass balance equations for the distillation unit. So equations are slightly more complicated than the flash unit and have 3 degree of freedom. So this is an important thing to note down. In case of distillation unit, we have 3 degree of freedom. So for determining the mass balance, we require split fraction of the light component, light key component, and the split fraction of the heavy key component, and along with this we require to specify the overhead column pressure. With these three variables specified, we can completely specify the given distillation system. Okay, so the schematic of the distillation unit is given here. So feed coming in the distillation unit, and the molar flow rate of the distillate coming out from the top is D, and the molar flow rate of the bottom product coming out is given by capital B here. So we wanted to represent this system into a uh, uh, simpler form as given in the right hand side. So here you can see that if there is a input, we wanted to represent that in terms of the output, which are calculated in terms of the split fraction. So this is what we are ultimately interested in. So let's look at some of the equations which are required in specifying the material balance for the distillation unit. So as I said, in order to simplify the equations, 5 types of the components are usually specified. So first component which we are assuming here is a component lighter than the light key. Then the second component is the light key component. Then we have the components between light keys and the heavy key. So these are distributed components. Then heavy key component, and the last one is components heavier than the heavy key. So you can see that with these 5 classifications we can simplify the equations immensely. So you can see that only 2 components we need to specify. One is the light key component, and then the heavy key component. All other are can be obtained easily. So so let's look at this particular figure. So this is the reboiler. So if we are taking the nth stage here, nth stage, so at the nth stage what we are having is so at the nth stage the mole fraction of the liquid coming in the nth stage is this, and the mole fraction of the vapor going out from the nth stage is ykr. So xk n minus 1 is same as ykr. So mole fraction of the liquid coming in the nth stage and the mole fraction of the vapor going out from the nth stage, both are taken same. So in this case the equilibrium relations we are using are the same relative volatility equation we are using. So at the nth stage the relative volatility is defined here is as uh, mole fraction of the light key component in the reboiler divided by mole fraction of the heavy key component in the vapor phase in the reboiler, and these are related to the mole fraction of the light key component in the liquid in the reboiler and mole fraction of the heavy key component of the liquid in the reboiler, and these are related using the relative volatility. So here relative volatility alpha Lk Hk is nothing but the relative volatility of light key component with respect to the heavy key component. Remember we are saying that this light key component and this heavy key component we are going to specify initially. Now this is at the nth stage. Now what will be at n minus 1 stage? At n minus 1 stage this same equation we can represent in the n minus 1 stage, which can be written as ylk n minus 1 divided by yhk n minus 1. This is nothing but the ratio of the mole fractions of the light key component and the heavy key component in the vapor phase, and that is represented as alpha Lk Hk into x Lk n minus 1 divided by x Hk n minus 1. Okay, so this is what we have written. Now you can see that in this case this x Lk n minus 1 and x Hk n minus 1, this we can represent as y Lkr and x Hkr, isn't it? Because x Lk n minus 1. So see, if you are looking at n minus 1 stage, whatever is coming in the n minus 1 stage in the liquid phase, and whatever is going from the n minus 1 stage, so that will be the mole fractions of the liquid phase and the vapor phase will be same. Here you can see the mole fraction of the liquid coming in the J J minus 1 stage should be same as the mole fraction of the vapor going out from the J minus 1 stage, isn't it? So with the same concept here, we can represent xlk n minus 1 as ylkr. Remember this xlk n minus 1 is same as lkr, and similarly xhk n minus 1 is same as xhkr using this particular equation. So with this we can replace this xlk n minus 1 divided by xhk n minus 1, and once we have replaced that by ylkr by xhkr, this ylkr and xhkr are again represented in the form of relative volatility and xlkr divided by xhkr. Okay, so in this manner you can see that at n minus 1 stage what we are ultimately going to get is ylk n minus 1 divided by yhk n minus 1 is given as alpha lk by hk square into xlkr divided by xhkr. So if we continue the induction till the stage 1, what we get is ylk1 divided by yhk1. This is nothing but the ratio of the mole fraction of light key component in vapor phase in the stage 1 divided by mole fraction of heavy key component in the vapor phase in the stage 1. So this can be represented as alpha lk by hk raised to the power nm. Here nm is nothing but the minimum number of stages required multiplied by xlkr by xhkr, and this xlkr by xhkr are nothing but what? These are nothing but the mole fraction of the light key component in the reboiler, and this is nothing but the mole fraction of the heavy key component in the reboiler. So again ylk1 and yhk1, using this particular relation we can write down ylk1 by yhk1. This can be represented as xlkd and xhkd. So what we are saying is at the stage 1, the mole fraction, remember in this case ylk1 is what? Ylk1 is nothing but ylk1 is nothing but in this case the vapor going out from the stage 1, isn't it? So remember, vapor going out from the stage 1, mole fraction of that is same as the liquid mole fraction of the liquid coming in the particular stage. So the liquid coming in is what? Distillate, isn't it? So clearly ylk1 is same as xlkd and yhk1 is given as xhkd. Okay, so now this is what the equation we have obtained. Now this particular equation is further simplified. So ylk1 is nothing but, or xlkd is nothing but what? It is nothing but molar flow rate of the light key component in the distillate divided by total amount of distillate, isn't it? Similarly xhkd will be what? It will be nothing but the molar flow rate of the heavy key component in the distillate divided by the total amount of distillate, isn't it? Similarly ylkr is nothing but what? It is nothing but the molar flow rate of the light key component in the bottom product divided by total bottom product. Similarly xhk is nothing but molar flow rate of the heavy key component divided by the total bottom product, isn't it? So now with this we can further simplify this particular equation as dlk by blk, and that is given as alpha lk by hk raised to the power nm into dhk by bhk. We again can rearrange this dhk. So this dhk is taken here from here to here, and this blk is moved in the denominator. So we have represented this equation as dlk by blk is given as alpha lk by hk raised to the power nm into dhk by bhk. So you can see that this particular term is now with respect to the light component, and the second term is with respect to the heavy component. Now dlk by blk is what? Dlk is nothing but the amount of molar flow rate of the light key component in the distillate. blk is the molar flow rate of heavy key component in the molar flow rate of the light key component in the bottom product. So you can see that this we can write down as zeta Lk divided by 1 minus zeta Lk. Remember, dLk can be represented as zeta Lk into inlet flow rate, isn't it? Similarly, BLK can be represented as 1 minus zeta Lk into inlet flow rate, and that inlet flow rate is common, so that will get cancelled out. So we can write down this as dLk by BLK is given as split fraction of the light key component divided by 1 minus split fraction of the light key component for the top products. Okay. Similarly, for the heavy key component also we can write down DHK by BHK as zeta HK divided by 1 minus zeta HK. Now this equation is extremely important, because now we can rearrange this equation and we can find out what will be the minimum number of stages required. So minimum number of stages required we can calculate by using this equation by rearranging. That is given as ln zeta Lk divided by 1 minus zeta Lk, and this entire thing, this entire factor divided by zeta Hk divided by 1 minus zeta Hk, and this equation is called as Fensky equation. So this Fensky equation is going to find out the minimum number of stages required in the distillation column when we are assuming the equilibrium relationship. Okay, so again this particular equation which we have obtained here, this particular equation we can further rearrange to calculate the split fraction of other components. Remember, in this case zeta Lk and zeta Hk, these are nothing but the split fraction of light key component and heavy key component. But remember, between light key component and heavy key component there are distributed components. So there are different components present, and we wanted to find out the distribution, we wanted to find out the split fraction of these distributed components. So we can rearrange this equation to calculate the split fraction of the different components, those are present or those are distributed between light key component and heavy key component. Okay, so zeta k we can directly obtain by using this equation by replacing this Lk by just k. If I replace Lk by k and rearrange this entire thing, we can get zeta k. So zeta k is nothing but the split fraction of any component between light and heavy, and in this case this alpha k is nothing but what? Alpha k is nothing but the relative volatility of the kth component with respect to the heavy key component. So this word heavy key component here is very important. This alpha has to be calculated with respect to the heavy key component. So once we have obtained this equation, our analysis gets simplified immensely. Now we have obtained these two equations, this equation number 1 and this is equation number 2. Now you can see that these two equations, if I put Nm equals to 1 in this equation turn out to be the same equation what we have seen for the flash unit calculations. So for flash unit, remember we had zeta Hk divided by 1 plus alpha k minus 1 into zeta Hk. So this Nm, if we get minimum number of stages, if we use equals to 1, then it becomes the flash unit. Okay, another important thing to note down here is, so see, in this case whenever we are doing the calculation for the distillation unit, the components lighter than the light key, remember we have specified the zeta Lk and zeta Hk, which are corresponding to the light key component and the heavy key component, isn't it? So anything lighter than the light key, for that we are taking this zeta k equals to 1. So we don't need to worry too much about those components, isn't it? For light key component, this value has to be specified by the user. Very often we take a value of zeta k for a light key component equals to 0.99, isn't it? And for all other components between light key and heavy key, we calculate the split fraction using the same equation, using this particular equation, and then for a heavy key component, again we are specifying the value of zeta Hk. So typically the value is used equals to 0.01, isn't it? And anything heavier than this heavy key component, for all those components the split fraction is equals to 0. Okay, so with this, now our calculations are going to become immensely simplified. So okay, in addition to the split fractions of the key components, specifying the pressure or temperature of the top of the column is needed. However, when we are specifying the temperature and pressure, there are different constraints need to be satisfied. Okay, so temperature has to be such that uh, constants with respect to the dew point, bubble point, calculations for the condenser as well as reboiler has to be taken into the consideration, and those constants we will see little bit in more detail when we look at one solved example. So in this case, the constant is this. The constant is the cooling water temperature. We have to take the cooling water temperature as close as the ambient temperature, because the large amount of cooling water need to be used in the distillation operation, and if we have the cooling water temperature as close as room temperature, then the utility cost decreases significantly. So bubble point temperature of the condenser has to be greater than the cooling water temperature. This is the first constraint. Second constraint is the dew point temperature of the distillate, or dew point temperature at the condenser should be greater than the bubble point temperature. Then the bubble point temperature of the reboiler should be greater than this dew point temperature of the condenser. Again, the dew point temperature of the reboiler has to be greater than the bubble point temperature of the reboiler. And finally, the steam temperature, the temperature of the steam that is used in the reboiler should have a temperature greater than the dew point temperature which is present in the reboiler. So these constants has to be satisfied. Now just look at some simple calculations here. So you can see that remember that we said that the cooling water temperature should be around the ambient temperature, typically around 30 degree. If you take that becomes 303 Kelvin, and if you take delta T of 5 degrees, so around this bubble point temperature should be around 310 or so. It should be greater than 310, something like that. Okay, again we have to select the bubble point temperature of all the components below the critical temperature of the mixture. So in this case, the bubble point temperature for all the components should be less than equals to the critical temperature of the mixture. And critical temperature of the mixture you can calculate, critical temperature of each component we can get, and that multiplied by corresponding uh, 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 mole fractions. So this weighted value is taken as the average uh, 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 critical temperature of the mixture. So bubble point temperature of each component should be less than this. Why? Primarily because we wanted to condense the uh, components which are there in the condenser, isn't it? So you can see that this is not always easy to maintain. Again, another requirement is another requirement here is the pressure inside the column. Pressure inside the column should be greater than 1 atmosphere, isn't it? In this case, you can see that the bubble point temperature has to be less than the critical temperature of the mixture. In this case, we want to have the pressure greater than 1 atmosphere, primarily because if we have a pressure inside the column less than 1 atmosphere, then we require a higher thickness of the vessel, and you require the additional cost. Now satisfying all these constants are not easy, primarily because very often we have non condensable gases which cannot be condensed in the condenser. Sometimes we have a non-volatile components which cannot be vaporized in the reboiler, isn't it? So clearly satisfying these constants are not easy, and in such cases what we do is we use a partial condenser or partial reboiler. So when we use a partial condenser or a partial reboiler, these units primarily uh, uh, perform a action similar to the flash unit. Okay, so not everything is getting condensed or not everything is getting vaporized, only the part of that is getting condensed or vaporized. So we can take them as a separate flash uh, unit calculation, as a flash unit calculation. Okay, so you will appreciate this concept when we will see one solved example. So in this case, what we are looking at, we are looking at the separation of benzene, toluene, orthoxylene mixture in the distillation column with 99% recovery of the benzene at overhead and 99.5% recovery of the orthoxylene in the bottom stream. So benzene and orthoxylene are the light and heavy keys that we have already specified. Okay, and the data given is as follows. So here you can see there are three components: orthoxylene, toluene and benzene. We have represented them as component 1, component 2 and component 3. Their molar flow rate is given as 50 kilomole per hour. So the molar flow rate of toluene is given as 30 kilomole per hour and molar flow rate of benzene is given as 20 kilomole per hour. Again, the equilibrium constants are given here. So equilibrium constant for orthoxylene at 386 Kelvin and 1 bar is given as 0.405. We can calculate this equilibrium constant again using the Antoine equation. So by using this Antoine equation we can obtain the vapor pressure. So we can obtain the vapor pressure by putting this is a temperature here, by replacing T by 386 we can obtain P1 naught, which is nothing but the vapor pressure of the orthoxylene at the given temperature. Once we get the vapor pressure of the orthoxylene, we can obtain the equilibrium constant K1 as P1 naught by P. So using this equation we can obtain the equilibrium constant, which comes around 0.4. Okay, so same is taken here, 0.405. In a similar way, you can see that uh, the equilibrium constant for the toluene is calculated again using the Antoine equation. So this is the same Antoine equation which we have seen in the previous example. Remember, one example we have solved in the last class, same Antoine equation we are using here. So with that equation we have obtained P2 at 386 Kelvin. So at 386 Kelvin, the P2 naught, which is nothing but the vapor pressure of the component 2, which comes around 800 mm of Hg, and from this we can obtain K2. So K2 is P2 naught by P. So here P is 1 bar, so that is around 750 mm of Hg. So with this we can again calculate the equilibrium constant, which comes around 1.079. Also the equilibrium constant of benzene is obtained as 2.50 using the same calculation by using the Antoine equation. Once we have obtained these equilibrium constants, so equilibrium constant of particular component divided by the equilibrium constant of the another component, that gives you the relative volatility. So in this case alpha Lk by Hk is nothing but what? Equilibrium constant of the equilibrium constant of the given component divided by equilibrium constant of the heavy key component, that will give you relative volatility. So in this case K1 divided by K1 is 1. Similarly the relative volatility here will be what? Here will be K2 divided by K1. So K2 divided by K1 if you do, so 800 divided by 300, that comes around 2.669. Similarly the relative volatility for benzene can be obtained as K3 divided by K1. So K3 is around 1915.38 divided by 300, that comes around 6.209. So all these values in the table we can calculate by using the Antoine equation. Now remember, in the distillation calculation we have to specify the split fractions for the light key component and the heavy key component. In this case the light key component is benzene, isn't it? So that is getting separated at overhead, so it's a light key component, isn't it? So its split fraction is given as 0.99, sorry 0.99. This is the benzene, correct? And the heavy key component is orthoxylene, which is separated at bottom and which has the recovery of 99.5%. So that means in the top product how much will be the amount? At the top product it will be 0.005. Now we know zeta 3 and we know zeta 1. We know this is zeta 3 is nothing but what? Zeta 3 is nothing but zeta Lk, isn't it? Zeta Lk light component, and zeta 1 is nothing but what? It is nothing but zeta Hk. So we know zeta Lk and zeta Hk, and we also know the relative volatility of the light key component and heavy key component. Now light key component is what? Light key component is benzene, heavy key component is orthoxylene. So clearly the zeta Lk by Hk value we need to use is this 6.209. Now with this, in this equation everything is known. We know zeta Lk, we know zeta Hk, we know relative volatility of the light key component with respect to the heavy key component. So we can put all these values. By putting all these values, what we get is the number of distillation stages required or number of trays required are 5.4153. Once we have obtained this number of minimum number of trays, this is the Fensky equation, this is the famous Fensky equation. By using this number of stages, we can now calculate the split fractions for different components. Remember, between light key component, this is the light key component and this is the heavy key component. Between this light key component and heavy key component, the distributed components present is tauline. In this case, only one component is there, tauline. So we have to calculate the split fraction of tauline. So split fraction of the tauline we can obtain using this equation, where alpha is calculated as the relative volatility of tauline with respect to the light key component, with respect to the heavy key component, which is nothing but orthoxylene. So in this case, zeta 2 is given as alpha 2 by 1 raised to the power nm divided by 1 plus in the bracket alpha 2 by 1 raised to the power nm minus 1 into zeta 1. So here nm is raised to the power. Okay. So we now can put all the values here and we can calculate what will be the split fraction for the tauline, and that comes around 0.505. Now with this calculation we have now obtained what will be the split fraction for the light key component, which is 0.99. What will be the split fraction for the heavy key component, which is 0.005, and we have also obtained the split fraction for the distributed component, which is 0.505. Now with this we can now do our mass and mass balance for vapor and liquid. Okay, so in this case these split fractions we have already obtained. Okay, now we can calculate how much will be the light key component in the distillate, how much will be the light key component in the bottom product. Similarly, how much will be the values of different components in the distillate and the bottom product, that we can calculate. So D1 is nothing but what? D1 is nothing but the, remember in this case D1 is with respect to the orthoxylene. Orthoxylene is a heavy key component. So we are looking at how much will be the molar flow rate of the orthoxylene in the distillate, that we can obtain directly by multiplying the corresponding split fraction into the feed rate. Feed rate is what? 50 kilomole per hour. So 50 into 0.005, that gives me the amount, that gives me the molar flow rate of heavy key component in the distillate. So that comes around 0.25 kilomole per hour. Okay. Now since this much amount of orthoxylene is going in the distillate, so remaining will be going in what? Remaining will be going in bottom product, isn't it? So we can obtain B1 as the total feed rate minus whatever is going in the top product, isn't it? So 50 minus 0.25, that gives me 49.75. This will be the amount of orthoxylene going in a bottom product, isn't it? So B1 here in this case nothing but what? 49.75 kilomole per hour present in the bottom. Similarly, D2 is nothing but what? Distributed component, which has the split fraction of 0.505. So 0.505 multiplied by the feed rate is 30, that gives me 50.15. So this is nothing but the molar flow rate of tauline in the top product, isn't it? And we can calculate what will be the molar flow rate of the tauline in the bottom product just by doing the mass balance. So which is nothing but 30 minus 50.15, that gives me 14.85. So this is nothing but the amount of tauline that will be present in the bottom product. Similarly, we can calculate for benzene. So benzene is a light key component, so its split fraction is given as 0.99. So 0.99 multiplied by the feed rate, which is 20, so that gives me 19.80 kilomole per hour. This much amount of benzene will be in the top product, and whatever is the remaining with respect to the feed rate, that will be in the bottom product. So in the bottom we will get 0.20 kilomole per hour. So once we have obtained D1, B1, D2, B2, D3, B3, now we can perform the bubble point calculations at the top. Remember, we have to check the temperatures, isn't it? We have to check the temperatures, whether the temperature and pressure which we have started with. Remember, in this case, this is the temperature and pressure we have started with. We have to check whether these values are correct or not. These are making sense with respect to the given data or not. Okay, so now in this case, once we have obtained D1, D2, D3, remember this entire, so here D1 is what? Molar flow rate of the component 1, D2 is the molar flow rate of the component 2, and D3 is the molar flow rate of the component 3 in the top product. And this entire thing has to be condensed. If you are taking the total condenser, all this D1, D2, D3 has to be condensed, because that's a total condenser. Everything has to be condensed. So now for condensing, let's, in this case, remember what is the abundant component present in the distillate. The abundant component present in the distillate is benzene, isn't it? So we can obtain the relative volatility of all the components with respect to benzene, with respect to the condenser. So all these calculations are with respect to the bubble point calculations at condenser, okay. So now when D1, D2, D3 are condensed in the total condenser, the mole fraction in the liquid phase will be what? X1, X2, X3. That we can directly obtain from D1, D2, D3, isn't it? So X1 will be given by what? D1 divided by D1 plus D2 plus D3. So we can put D1, D2, D3 in this particular equation, and we can obtain the mole fraction of the component 1 in the distillate. So that comes around 0.007. Similarly, X2 is the mole fraction of the component 2 in the condensed distillate, so which will be D2 divided by D1 plus D2 plus D3. So that comes around 0.430. And similarly, we can calculate for X3. Remember, X3 is nothing but what? X3 is a benzene. So benzene, the highest mole fraction will be with respect to benzene, which comes around 0.562. Now again we can calculate. Remember, in this case, since the benzene is abundantly present, it's a plentiful component, we have to calculate the relative volatility with respect to benzene here, only for this bubble point calculations here at the condenser. Remember, when we are doing the bubble point calculations for the condenser, now we have to do the calculations based on the component which is available in a plentiful amount. Okay, so in this case, the benzene is the component which is present abundantly. So now, since the benzene is the component which is present abundantly, we have to calculate all the alphas with respect to the third component, which is nothing but benzene. So that's why we are calculating alpha 13, alpha 23 and alpha 33. So this is nothing but what? This is nothing but the relative volatility of the orthoxylene with respect to the benzene, and that will be given by what? That will be given by just the ratio of the equilibrium constant. So that is given as K1 by K3. We have already calculated K1, and we have also calculated K3. Look at the table. In the table, we have already calculated K1 and K3, isn't it? So we know what is the value of K1 and we know what is the value of K3. So K1 by K3, that is nothing but what? 300 divided by 1915.38. So in this case, K3 is 2.55 and the K1 is 0.4. So 0.4 divided by 2.55 is going to give me alpha 13. So that comes around 0.16. Similarly, we can calculate alpha 23, which is nothing but K2 divided by K3. So that is 1.07 divided by 2.55. These are also we have calculated in the table. So see, K2 is 1.07. So 1.07 divided by 2.55, 0.42, and for the last component, that will be equals to 1. So once we have obtained the relative volatility with respect to the abundantly available component, then we can find out the average values of relative volatility. So average values of the relative volatility with respect to the mole fractions we can obtain. So alpha bar we can obtain. So, and P divided by alpha bar is going to give us the bubble point pressure. Okay, the pressure, vapor pressure at the bubble point, that is what we are going to get. So vapor pressure of the benzene comes out to be 1008.4 mmHg. Now this particular value of the vapor pressure, again we can back substitute in the corresponding Antoine equation, and we can back calculate the temperature. So temperature comes here 362.17. So you can see now this 362.17, this particular temperature is greater than the cooling water temperature. Remember, what is the cooling water temperature we need to maintain? The cooling water temperature should be roughly, so bubble point temperature should be roughly greater than equals to 310 Kelvin. And you can see that in this case the temperature comes around 362, which is greater than the cooling water temperature. Okay, so the temperature and the pressure which we have assumed here, this temperature and pressure we have assumed here are okay in terms of the condenser. Now we have to do the calculation with respect to the bottom. Okay, so that we will look at in the next slide. So again remember, so this one temperature we have done. Now we can do even a dew point calculation, because dew point calculation is going to give us the overhead vapor temperature. So for dew point calculation, again we can obtain the vapor pressure of the abundantly available component, that will be Pn here. Okay, so we can obtain that uh, so Pn not T we can obtain as P into summation of Yk by alpha Kn. So that comes around 1222.16 mmHg. We can back substitute in the original equation, and we can find out the temperature, and temperature comes around 368.94. Okay, so you can see that this particular temperature is greater than this is the dew point temperature. This particular temperature is greater than the bubble point temperature. So bubble point temperature is 362, and that is 368. So you can see that in this particular equation this term is satisfied, even dew point temperature is higher than the bubble point temperature, so this condition is also satisfied. Now let's look at the calculation with respect to the reboiler. So again same, the mass balance, uh, the flow rates, molar flow rates which we have obtained for distillate and bottom product are given here. These are the same values which we have calculated here. So these are the same values which we have calculated here. So the same values we are now using for calculation at the bottom product. So for bottom product we should be looking at B1, B2 and B3. So with respect to this, now we can find out what will be the mole fraction. So X1, X2, X3. So in this case now we have obtained X1, X2 and X3. These are the mole fractions. So X1 is coming out to be 0.767, X2 is coming out to be 0.230, and X3 is coming out to be 0.0031. So you can see that in the bottom the abundantly available component in this case is orthoxylene, isn't it? So that is why the mole fraction of the orthoxylene is coming at 0.767, and the least amount of component present is benzene, so it has the mole fraction of 0.0031. So clearly, since the orthoxylene is present abundantly, we have to do the calculations with respect to the orthoxylene. So relative volatility, now in this case we have to calculate with respect to orthoxylene, and orthoxylene is component 1, so that's why we are calculating alpha 11, alpha 21 and alpha 31. So alpha 11 in this case will be K1 by K1, that is just 1. Alpha 21 will be K2 divided by K1, so that comes around 2.662, and alpha 31 is K3 divided by K1, so that comes around 6.209. So now with these three values, again we are going to perform the bubble point calculation. So bubble point calculation, again we are calculating the average relative volatility, and P divided by average relative volatility is giving me the vapor pressure of the abundantly available component. So that is orthoxylene, so which comes around 536.28, and then we can use the corresponding Antoine equation. So with the corresponding Antoine equation we can calculate what will be the temperature. So temperature comes around 405.37. So this is the bottom temperature. Okay, again we can do a dew point calculation. So from dew point calculation we calculate the average value of this, the vapor pressure. So vapor pressure comes around in this case 640.08 mmHg, and again we are doing a back calculation using a Antoine equation, and the temperature comes around 411.2 K. So now what we can conclude here? We can conclude here is that all your temperatures, you can see that the bubble point temperature of the condenser is greater than the cooling water temperature. The dew point temperature of the condenser is greater than the bubble point temperature. Then the bubble point temperature of the reboiler, which is nothing but this, is greater than the dew point temperature of the condenser. Again, the dew point temperature of the reboiler is greater than the dew point temperature, bubble point temperature of the reboiler. And finally the steam temperature should be greater than this. In order to have a uh, operation here, satisfactory operation, we need to have a steam with a temperature greater than 411.2 Kelvin. Okay, so clearly in all these calculations we have taken a complete condenser and complete reboiling. Okay, but in a several real life practical problems we usually have a non condensable gases, and also we have non vaporizing components. So in such cases we have to use a partial condenser and partial reboiler. So in those cases one additional calculation as a flash unit we have to do it for the distillation condenser and reboiler. So those additional calculations we have not done here. Okay, but can be done easily. Now let us extend the analysis to develop the linear mass balance equations for the another unit. So another important unit is a absorption unit. So absorption can be modeled as a cascade of equilibrium trace similar to what we have seen in distillation unit. However, here the assumption of equilibrium is weak, and one has to use the efficiency in the calculation, absorption efficiency, that we have not looked at here right now. But for a better calculations one has to account the stage efficiency or tray efficiency here. So absorption is the key recovery of component from the vapor to liquid, and reverse of that is called as stripping, where recovery of the key component from liquid to vapor. Okay, so both absorption as well as stripping we are going to look at. Okay, now unlike the flash unit where only 2 degree of freedom was there, then we have looked at distillation column where we had 3 degree of freedom. In absorption unit we have 4 degree of freedom. So that means 4 values, 4 variables we have to specify in order to solve the material balance. So equations are slightly more complicated than distillation unit and have 4 degrees of freedom. For determining the mass balance we have to specify pressure on the equilibrium tray, we have to specify the number of trays and temperature and flow rate of the absorbing liquid. So this we have to specify. Now a typical schematic given here is shown, where you can see that the liquid which is coming in the absorption unit is the molar flow rate of the liquid is capital L naught. Again we have uh, uh, multiplied L naught to a mole fraction x naught. So here mole fraction x naught is nothing but the mole fraction of the key component. Okay, so that k which is with respect to the key component, or n with respect to the key component, that we have omitted here. So small L naught is nothing but the molar flow rate of the component, a particular key component coming in the absorption unit. Okay, so the another inlet is the vapor coming, the vapor from the previous equipment is entering into the absorption unit. So that is represented by Vn plus 1, capital Vn plus 1, that is molar flow rate of the vapor entering in a distillation unit. Okay, and the corresponding the molar flow rate of the key component is given as small Vn plus 1. So here the subscript or superscript denoting the key component, which we have used small n everywhere, that we have omitted here. Okay, so in a absorption unit there will be several stages will be there. So in this case we have shown 1 to n stages. Now with respect to any equilibrium stage, I, how the inputs are there and how the outputs are there, those are represented in the second figure. So here you can see that we have taken a equilibrium stage I. So the input to the I stage is small l I minus 1. Again the input is small v I plus 1, that is the input, and the outlet from this equilibrium stage is small vi and small li. Okay, so in this case, the if I have to write down the mass balance, so mass balance in this case will be vi plus 1 plus li minus 1, and that should be equals to vi plus li. This will be the mass balance. Now there are several, interesting concepts are there, we will cover that. So remember, in this case, in this entire mass balance, we have to account the equilibrium relationships. So how the equilibrium relations are accounted? So equilibrium relation is given here, you can see. So this equation is actually what, if I rearrange this equation is nothing but what, ki li by li, and the right hand side will be vi small vi by capital Vi. So this is nothing but what, this is nothing but li by small li by capital Li is nothing but xi. So that is nothing but ki xi, and that is given as yi. So this is the equilibrium relation which we are using everywhere. So the same equilibrium relation is used here, but now represented in a different form. So we have rearranged this equation slightly, and we have defined Li, capital Li divided by ki capital Vi. This entire bracket term, we have represented as absorption factor Ai. So with this simplification, uh, the equation now can be represented simply as Li is given as AiVi. Li is given as AiVi. Now let's look at the mass balance here. So if we take the uh, top tray, so if you take the stage 1 or top tray, so things coming in for the top tray will be what, if I take a top tray, so in that case this will become, for a top tray, let's say this is the 1, so for 1 this will become L naught, this will become V1, this will become V2, and this will become L1. Remember, so in this case, if I use this notation in the mass balance, what I'm going to have, I am going to have Li plus, sorry, L1 plus V1 is equals to L0 plus V2. So that is what is written here. Now in this case, you can see that uh, L1 will be given by what? L1 will be given by A1 V1. So we can replace this L1, we can replace by A1 V1, and V1 is already there, so we can take that V1 common, so it becomes A1 plus 1 into V1, and that should be equals to this entire bracket term, isn't it? Now we can further rearrange this equation. So after rearranging, we can obtain this V2. This V2 can be obtained as this entire term minus L0. So this is what we have obtained. Okay, now once we have obtained this, now we can write down this mass balance for any stage I. So any stage I, we can write down this mass balance like this, isn't it? Vi plus 1 is coming in, plus Li minus 1, isn't it? And that should be equals to Li and Vi, isn't it? So we can rearrange this equation, so we get Vi plus 1 is given as Li plus Vi minus Li minus 1, and in this particular case, this Li can be replaced by AiVi. I can put that AiVi, so I can take this Vi common, so that becomes Ai plus 1 in the bracket, and outside we will have Vi, and this Li minus 1 will be what? It will be nothing but Ai minus 1 into Vi minus 1. So that is what is written here. Now let's look at these equations for V3 and V4. So V3 is the third, V3 is nothing but what, we are trying to write down the expression for V3 similar to this by using induction. So V3 will be what, V3 will be nothing but A2 plus 1 into V2 minus A1 V1, isn't it? Now in this case V2, this is the V2. Now V2 we have already obtained the expression for the V2 is this. I can put this expression in place of V2. So if I put that, this is the equation we have obtained, isn't it? And now even uh, this particular equation we can rearrange little bit. Again here V1 will be what? V1 will be nothing but what? V1 we can obtain directly V1 as A2 plus 1 L naught, isn't it? Remember that is what in this case V1 is what? V1 is nothing but here if we look at this expression here, in this case V1 we can represent as uh, this entire term we can rearrange, this entire term we can rearrange. V1 is there, and all these terms here, this V1 is there common, and here also another V1 term is there. So we can collect these common terms and rearrange this entire equation in terms of V1 and L naught, and finally what we get is A2 A1 plus A2 plus 1 into V1 minus A2 plus 1 L naught, isn't it? This is what we have obtained for V3. Similarly we can write down for V4 again the expression from the starting expression from this, so that will be A3 plus 1 into V3 minus A2 into V2. Now this V3 we can replace by this V3 which we have obtained here, and this V2 we can replace by this V2. So we can put those here, and further simplifying what we get is V4 is given as A3 A2 A1 plus A3 A2 plus A3 plus 1 into V1 minus A3 A2 plus A3 plus A plus 1 into L naught. So you can see that for all the uh, uh, variables here, so V1 V2 V3 V4, you can see that we can write down the expression by induction. So for nth variable Vn plus 1, Vn plus 1 is the, remember Vn plus 1 is the input, remember this Vn plus 1 is the input, isn't it? So we are starting from stage 1 and we are finally reaching to obtain Vn plus 1. So Vn plus 1 can be written by induction, and that can be given as 1 plus an into an minus 1 plus, and this summation goes all the way to the last term. Remember every subsequent term has one additional term. So here starting from 1, then A3, then A2 A3, then A1 A2 A3. So same concept is used here. We are looking at n plus 1. So you can see that the last term will start from an, and that will goes all the way to A1 here. Okay, but look at the second term here. It is going from, in this case you can see that uh, so this last term is missing here. Okay, so the same thing is written here. Okay, so slightly modified term we are getting with respect to L naught. Okay, so once we have obtained the expression for Vn plus 1 by using induction, now this entire equation we can write in terms of summation. So this is the equation which we have obtained. This entire equation we can write down in the form of summation. So Vn plus 1 can be obtained as so see, to simplify this particular equation, we are again assuming that all these absorption factors, we are assuming that the average absorption factor is there, and this A1 A2 all the way to An, these are equals to average absorption factor. So if we use this particular assumption, we can simplify this original equation and we can write down this original equation in terms of summation. So you can see that we have written this entire term as ae raised to the power I into v1, isn't it? So this summation, this particular term is nothing but what? Every stage you can see that the I is coming in the power. So if you are having all these absorption coefficient equals to each other, in that case there will be a, so see in this case this will be what? 1 plus ae plus ae square, and that summation goes all the way to ae raised to the power n, isn't it? Similarly, this second term will be what? 1 plus AE square, and that summation goes all the way to AE n minus 1. Okay, so the same thing is represented in the summation form here. Now again further to simplify this entire summation is represented by another constant bn, beta n. So this another constant beta n, if I multiply this beta n by 1 minus AE, isn't it? So if I multiply this entire equation by 1 minus AE, what we can get? So let's say 1 minus AE into beta n. So what we are going to get? We are going to get the first term will remain as it is, isn't it? So that will be I equals to 1 to n AEI. This is what we are going to get in the first term, and the second term will be what? Second term will be AE into I equals to 0 to n, I equals to 0 to n AEI, isn't it? Correct. So minus this, correct. So now this AE is multiplied here, so this entire equation has 1. So that 1 will get converted to AE. So this summation will start from I equals to 1 to n. So that's what we have obtained, and that will go up to n plus 1. So this term, the second term will be nothing but this. So this is what we have obtained. Now we can rearrange this term. So we can rearrange this term, and so see, if I subtract this entire term from the first term, what I am going to get? I am going to get just 1 minus AE raised to the power n plus 1. This is what I am going to get, and this is what is put here. So this entire term is nothing but 1 minus AE raised to the power n plus 1. Okay, so from this I can now rearrange and I can find out beta n. So beta n comes out to be 1 minus AE raised to the power n plus 1 divided by 1 minus AE. So I can calculate, if I know the absorption factor, then I can calculate beta n. Okay, if I know the absorption factor and the number of stages present, then I can calculate beta n. So with this simplification, this equation can be written as Vn plus 1 is given as beta n V1 minus beta n minus 1. Remember, in this case it is going n minus 1, so that becomes beta n minus 1 into L naught. Also the overall balance is what? The vapor coming in the absorption unit is Vn plus 1. The liquid coming in the absorption unit is L naught with respect to a component, and whatever is going out, the liquid going out from the absorption unit is Ln, and the vapor going out from the absorption unit is V1, and all these terms are with respect to the component. Okay, so this is the overall balance. So now we can further calculate this AE. So there is a equation given by Edmiston. So what Edmiston is saying, that we can consider the A1 is the absorption unit for the top tray, and A2 can be considered as the absorption factor for the bottom tray, and if we know both these absorption factor, we can calculate the average absorption factor. So this average absorption factor, once we have obtained, we can put it in this equation and we can do the calculation, we can do the mass balance. Okay, so these are the all equations. Now with respect to this, remember, in all these equipments, ultimately what is our goal? Ultimately our goal is to represent input and output in the form of split fractions, because if we represent the output in terms of the split fractions, then calculations becomes immensely easy. Okay, so same thing we are going to do it here also. So far we have only formulated the important equations. Now again let's look at, so remember, what is the input? Input to the absorption unit is Vn plus 1, that is the input, isn't it? So the molar flow rate of the key component, now we have put the subscript superscript n here. So here superscript n basically representing the key component. So far we have omitted that, now we have started putting that as a superscript here, just to illustrate that it is with respect to the key component. So in this case you can see that Vn plus 1 is nothing but what? Vn plus 1 is nothing but the molar flow rate of the vapor coming in for the key component in the absorption unit. Okay, now we are specifying the split fraction. So R here is the split fraction. So 1 minus R, that will be the amount from this vapor will be absorbed by the liquid, isn't it? Correct. So R 1 minus R, we are uh, multiplying to this, so that will be giving me what will be the molar flow rate of the vapor coming out from the absorption unit. So V1 will be given as 1 minus R Vn plus 1, and the superscript we have represented in order to represent this equation for the key component. So here key component is N. So now this particular expression we can put in the original equation. Original equation was what? Original equation was Vn plus 1 is given as beta n V1 minus beta n minus 1 L naught. That is what the equation we have. That is what the equation we have derived. See, this is what the equation we have derived. Vn plus 1 is given as beta n V1 minus beta n minus 1 L naught. Here I have omitted the superscript. Here I have omitted the superscript with respect to the components. Now if I write down the equation for the key component, if you write down the equation for the key component, you can see that this is the equation for the key component. Here this V1, which is the output coming from the absorption unit, I can replace that by using this equation. So if I replace this V1 by using this equation, what we are going to get? We are going to get beta n 1 minus R Vn plus 1 raised to the power n minus beta n minus 1 L raised to the power L naught n. Okay, now I can substitute beta n and beta n minus 1. Beta n is given by what? 1 minus ae n raised to the power n plus 1 divided by 1 minus ae, and this is nothing but what? 1 minus ae raised to the power n divided by 1 minus ae, isn't it? And I can rearrange this entire equation. I can rearrange this equation and finally write down the expression for capital N. So the expression for the capital N is given as ln L naught raised to L naught plus Vn plus 1 R minus ae divided by L naught minus ae into Vn plus 1 1 minus R, and this entire thing is divided by ln ae. So what this equation is? This particular equation is giving what will be the minimum number of stages required in the absorption unit in order to have this much recovery. Okay, so we have obtained the minimum number of absorption stages. You can see that this equation can be simplified immensely. Remember, we can use a pure solvent as coming in. We can have a pure solvent coming in this particular case. Remember, this L naught need not be having any key component here. It could be a pure solvent. In that case, L naught will be what? L naught will be with respect to a key component. What will be L naught? It will be 0. So if we have, let's say, L naught equals to 0, if we have a L naught with respect to a key component equals to 0, this equation can be further simplified as the minimum number of stages required in a distillation unit can be obtained as ln R minus ae divided by ae into 1 minus R, and this entire term is divided by ln ae. So in this case, now remember, in the starting of the this absorption unit, I said that there are 4 degrees of freedom. So the first variable we have to specify is the split fraction R of the key component N. Then we have to specify the overhead column pressure. We have to specify the solvent temperature. So we have to specify the temperature with respect to capital L. Remember, capital is the molar feed rate of the solvent to the absorption unit. So we have to specify the solvent temperature. We can assume the isothermal operation in the entire absorption unit, and also we have to specify the absorption factor A. If we specify the absorption factor, we automatically able to calculate what will be the liquid flow rate which is coming in. Okay. So yes, thumb rule used is use the absorption factor equals to 1.4. So now let's look at the simplification of all the equations. So what are the steps required for solving the absorption mass balance? The first step is we have to identify the key component N, and then we have to specify the split fraction R. Typically the value is used 0.99, so that means what, we wanted to extract 99% of the key component from the vapor by using the solvent. That is what it means. The next parameter we have to specify is pressure, and then we have to specify the solvent temperature. Okay, remember that L naught we are using as, we can use the AE equals to 1.4, that is the thumb rule. So if you use AE equals to, that is the absorption factor, equals to 1.4, then we can calculate what will be the molar feed rate of the liquid to the absorption unit L naught. So L naught we can directly calculate by using this equation. Remember, AE is given as what, L naught divided by Vn plus 1 into Kn. So L naught Va divided by Vn plus 1 is there, isn't it? And this AE is equals to 1.4, so we can rearrange this equation. So after rearranging, what we get, L naught is given as 1.4 Vn plus 1 into 1 by Kn, isn't it? And 1 by Kn is what? Remember, what is the equilibrium constant? Equilibrium constant K is given by, equilibrium constant is given by what? Equilibrium constant is given by, in the last calculation we have seen, isn't it? So if we go back, in the table, you can see that how we have calculated the equilibrium constant. Vapor pressure divided by the total pressure. So the same expression is used here. Okay. So next step here is, so we can calculate L naught here. We can calculate L naught, and you can see that L naught decreases with increase in P. So L naught decreases with increase in P, and once we have calculated the L naught, then what we have to calculate is, we have to calculate the number of stages. Remember the Kremser equation which we have derived earlier. So same Kremser equation we can use, and we can calculate the number of stages. This equation gets simplified if you have a pure solvent. In that case, L naught for a key component is 0, and then we can get, and if you are using R equals to 0.99, typical value of N get around 10. Once we have got the number of stages required, then, so see, in this case, this AE is nothing but what, this is nothing but the absorption factor of the key component. But in the absorption operation, there are multiple components are there, so we need to calculate the absorption factor for other components. So absorption factor for other components are calculated using this equation. So AK here the superscript K represents the different components, so that can be given as, L naught divided by Vn plus 1, P divided by, so Kn is given as P divided by Pk naught T, isn't it? And that is given as 1.4 divided by, so see, this particular term can be written as, so see, L naught by Vn plus 1, if I put this L naught by Vn plus 1 into Kn, we can put 1 by 4, so we will have 1 by Kn term will be there, and 1 by Kn term will be nothing but what, alpha K by N. Okay. So with this this is the with this we can obtain the different values of the absorption factors for different components. So once we have got the absorption factor for different components, we can use this equation, and we can calculate the corresponding Bn and Bn minus 1. We can also calculate, in this case, Bn minus 1 for the kth component, that will be 1 minus Ak raised to the power n divided by 1 minus Ak, isn't it? Once we have obtained Bn minus 1 and Bn, we can use those in the mass balance equation, and we can calculate the corresponding mass balance. So V1 and Ln we can calculate by using this equation, we know. So see, this is the input, Vn plus 1 is the input, isn't it? And L naught is the input, correct? Similarly, in this case, Vn plus 1 is the input and L naught is the input. So by using input, we are actually calculating the output. What will be the output from the nth stage? So from the output from the nth stage will be the molar flow rate of the vapor coming out from the absorption unit, that will be given by Vk with respect to the component K. Similarly, the molar flow rate of the uh, uh, kth component, liquid in kth component from the nth stage, that will be this. So both these inputs from the absorption unit we can calculate, both these outputs we can calculate by using the inputs. These are the inputs. These are the inputs. Okay. So once, so this completes the mass balance. Now you can see that both these mass balance are linear equations. Okay. So that is what we were interested in, isn't it? We wanted to get the mass balance in the form of linear equations. Now once we have done this mass balance, what we have to do is we have to do a back calculation. We have to do a back calculation just to check whatever the pressure and temperature we have used, whether these are correct or not. So if the temperature of the liquid coming out from the absorption unit is too high, if the temperature of the liquid coming out from the absorption unit is too high, in that case the inlet flow rate of the solvent has to be increased. So capital L naught has to be increased. If significant amount of solvent is getting vaporized, if the solvent is getting vaporized in the absorption unit, isn't it? So outlet is V1. So let's say if there is a significant amount of solvent is vaporized, clearly in that case we have to increase the pressure and decrease the temperature. Another case could be if, let's say, the significant quantity of undesired components are absorbed. Remember, we wanted to get the absorption of the desired component, not the undesired component. So in that case what we have to do, we have to increase the temperature and we have to decrease the pressure, or we have to, otherwise we have to use the different solvent. So this is all about the mass balance for the absorption unit. So there is one more unit which is a stripper unit. Stripper unit is just a reverse of the absorber. So same equations what we have derived for the absorber are used in the stripper. Remember, in the stripper what we do, in the absorption unit we are actually absorbing the key component from vapor to liquid. In a stripper, reverse happening. So the key component is getting absorbed from, is stripped from liquid to vapor. Okay. So in this case my input will be what? Input will be the vapor. So that is why vapor is starting from V naught here. Remember, in the absorption column we have started with L naught. Similarly here it is started V naught. Okay. So based on that the entire terminologies are changed. So now here input is V naught, the input here is Ln plus 1, and the outlet from the stripper unit is Vn and L1. Okay. So again the same equilibrium relations we are going to start with, isn't it? So these are the same equilibrium relations which are nothing but what? Ki xi is given as yi. These are the equilibrium relations. So same equilibrium relation is used here, now rearranged in a different way. So in this case we have rearranged this equilibrium relation like this primarily because we wanted to represent the Vi k is now in this case is represented as Vi k is represented here as uh, uh, capital Vi Ki k divided by Lik, and this entire term we are representing as stripping factor. So this is represented as Si. So Vik is given as Si Lik. Now in the absorption unit we have, you can see that in the absorption unit the liquid flow rate we have represented in terms of the vapor flow rate. In this case we are doing a reverse, vapor flow rate we are representing in terms of the liquid flow rate. Okay. Now considering the split fractions of the key component N in the liquid, again similar to the Kremser equation which we have obtained in the absorption unit, in the stripper unit also we get another Kremser equation in terms of the stripping factor. Remember, here the stripping factors are used. Okay. So in terms of stripping factor, this is what we have obtained, where this capital N here represents the minimum number of stages required in the stripping unit to have a desired splitting ratio of R. Okay. Again we can use the stripping factor of 1.4, and based on that we can calculate what will be the initial flow rate. Remember, initial flow rate of the vapor V, isn't it? So that we can obtain using this equation. So by specifying 1.4, actually we are specifying the inlet flow rate. Okay, so similar type of calculation as we have done for the absorber unit, we will be doing it here, but now in a reverse way. So that is the only difference with respect to the stripper unit. So we will continue from this point in the next class, and we will look at how this concept of linear balances with respect to the different units like uh, reactor, stripper, mixture, splitter, absorption unit and distillation unit. These are the main important units which we see in the chemical processes. So how the linear balances with respect to these different units are used to solve the entire flow sheet, this part we are going to look at in the next class. So we stop here. Thank you.